Alright, 34. Yeah. 34 is a nice, quick, and easy problem. It's dealing with basically graphs of motion, which we've done back in chapter 2, and then kinetic energy, rotational kinetic energy. So we got a graph, omega versus t graph, the slope of which, I'm just going to do a rough sketch, the slope of which gives you the acceleration, right? The slope of a velocity graph gives you acceleration. So angular acceleration is the slope rise over run of a angular velocity graph. Luckily it's a straight line, so we can just do a rise over run like that. And so the rise, if you look on the graph on page 268 for number 34, you go up 9 and over 6. So that gives you 1.5 radians per second squared for the angular acceleration. That's part A. Piece of cake. Part B, what's the kinetic energy at t equals 0? Well, what we need to do first, they give us constraints. They tell us the kinetic energy at t equals 4. So Ke radial, that's R, radial at 4 seconds is 1/2 I omega squared. And so at 4 seconds, the kinetic energy is 1.6 joules. That equals 1/2 I. And then you look on the graph, and you see at 4 seconds, the kinetic energy is also 4. Sorry, the angular velocity blah, 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 is also 4 radians per second. Square that. Solve for I, and you get a moment of inertia, or radial mass, is another cool way to put it, of 0.2 kilogram meter squared. That mass doesn't change, so we'll use that in this next part. So Ke rotational at 0 seconds also equals 1/2 times the same rotational inertia, 0.2 that we just found, times omega squared. And looking at t equals 0 on the graph, you see that the angular velocity is -2. So this is going to equal 1/2 times 0.2 times -2 squared. And solve that out, and you get 0.4 joules. Piece of cake. Alright, next problem, 39.